we have made a myoelectric socket that is both flexible and strong enough to hold on to the load of whatever you put on it. So, right here we got nylon, but it's Tallman PCTPE. It's both flexible, but also very, very strong. Layer bonding is extremely good. And here the flexible part here, we have Ninja Tech Cheetah. So with this configuration, as you can see here, there's some segmentation going on here. For motions such as pronation and supination, with this design, it allows Chad to rotate as freely as possible, and basically, this part of his arm doesn't rotate as much as this upper hand here with this motion. So with this segmentation, allows for that motion. So also, Chad has wrist disarticulation. Sorry, I'm getting my words down. But so that means he has wrist motion still. So with this configuration, it allows him to have all the degrees of freedom that he naturally has. So unlike, whoa, that's rude. we didn't put those in yet. So, what was it saying?
We're talking about wrist disarticulation.
That's right. So with the raptor hands, I guess, the raptor hands that we used to have, when Chad needs to grab anything on the table that's lower than his natural body height.
Like one of these, like, you know, you got to kind of tweak your body a little and line up just right and grab, and then you have to do a forceful contraction and hold it to hold it. Whereas now, I'm able to kind of come in and guide a little bit better. Right here is a socket for a Bionic hand. So we did make the inside ring, but we custom fit a portion of the 3D printed part to fit that ring. And it fits the other hand as well too?
Yes. So
it's a modular device, so we're able to fit multiple different devices into it, which is the idea when you're using this in a lab for testing to understand the ability of myoelectric sensors to pick up when you're moving. Because if you have a sensor and it's stretching or being deformed over a surface, you're going to get a decrease in signal or perturbation of signal. So the idea that Marty was mentioning is that because of the rotation of the arm is limited at the bottom where the electrodes are, you don't get that displacement as much, and so you get a more accurate read. And you're not cross talking with muscle groups, so you're getting multiple degrees of freedom instead of just a single open and close. But you can do pinch, you could do pivot, you could do like full grafts, for example. So it just allows a couple of different degrees of freedom. And then you want to talk about the co-contractions? Like what you're doing with the co-contraction. So how do we make more degrees of freedom? So another question we're asking is, how can we make degrees of freedom that don't exist, right? How can we do that? So one of Marty's works that he is working on, he just isn't thinking straight. It's okay. So one of the things he works on, though, is providing those degrees of freedom and providing that. And so part of the co-contraction means I would flex my top and my bottom muscles, and that would tell intuitively a signal to change a command. So I would squeeze my arm really quick, and it would tell it to, okay, we're going to oppose. Or if I do a little code, like 2 squeezes within a certain amount of time, I can tell it I want to pinch now. So you can kind of train your body in that way as well to kind of allow more functionality. So, and then we have some pieces. I'm sorry, I put them all the way at the end of the table. If you guys want to pass around the printed nylon, is it the nylon head and then the PCTPE? Mm-hmm. So that's just the flexible materials. And how do we print this, Marty?
So we use.
Oh, yeah, but how's it printed? Is it printed, laying down?
So these, all the different parts are oriented different ways. The top adapter is printed flat, and nylon, as most of you know, is very, very hard to print with. It warps a lot, so we had to use heated bed up to like 110 degrees, and nozzle up to 150. So with Cheetah, we had to use.
Can you say the nozzle temperature again? You said the bed is 110 and the nozzle?
110. Nozzle for nylon is 250.
Oh.
And
So,
I use real small layer heights and got better results with warping. I don't know if
Okay.
0.05.
Mm-hmm.
Have you guys tried using Magigoo PA? That's specifically for nylon.
No, we have not.
Helps a lot.
But for support with the nylon parts, we use PVA, and
Okay.
that works very, very well.
Yep.
And
So
so,
the flexible portion, though, how's that printed?
so we used PLA for support for the flexible parts, and they're printed flat like this on the print bed. And for this part, we had a lot of trouble with this because it's very thin, and also just doesn't like to stick. So we used PVA as support as well, and that stuck really, really well.
So is that nylon?
This part and this part
Yeah.
are nylon. Yes.
Yeah.
So
Okay.
nylon and then the TCPT or
So this
Cheetah.
Cheetah. This is Cheetah. This is PCTP,
Which,
which is a nylon.
cheetah? What? Remind me what that is. Is that the
Ninja Tech.
82A softness or what?
I think it's
We looked at
supposed to
that.
be 95, but because of the thin, how thin it is,
Okay.
That
it's
was
a
the
little
only
bit softer.
flexible thing we could print on the Ultimaker.
Okay. All right.
Polymaker has a nylon
Oh.
that doesn't work.
We like Polymaker. They got some stuff.
What's that?
We like Polymaker.
The last
Yeah.
version,
All-in-one stuff.
Great stuff.
last version we used Polymaker Polyflex, but we found that Cheetah is a little easier to print with. So.
So I'm seeing what look like to me two wonderful, wonderful innovations. One is the notion of a flexible framework which will optimize the sensors. But the other is just the socket itself, which looks like it's pretty conformant, it's adjustable, and it allows a great deal of
What software did you use?
manipulation.
What did you make this in?
Do you guys know what mesh mixer is?
This is all
Mhm.
made in Mesh Mixer.
The whole thing?
The whole thing. The whole thing.
Actually,
Now,
Wow.
to what
Most-
extent
most
does it need to be customized for a given arm? How, if you wanted to cover most, let's say, teenage to adult arms, could you do with small, medium, or large? How many sizes do you
How do
think
we
you
start this process?
So-
what do we start with?
let's start with how we make this. First of all, we have to get a 3D scan. So we have a scanner, SkinX scanner, and we built a rig and everything to make sure that we have a good scan, because last time we scanned it, it wasn't very accurate. So once you have the good scan, put it into Mesh Mixer, offset, and make this socket, and then put
Like
a
a
little
general shape, and
personal
then you go
touch.
to work on it. Yeah.
But
But-
now that you've got the general shape, I'm about the same size as Chad. Could I put that on?
Okay. So, but everybody has different
Muscular
structure and everything.
Yeah.
So when I was designing this, I have about the same arm length as Chad. So I was able to take off this adapter piece and try it on and make sure that everything is comfortable, feels nice, so I can give it to Chad and for him to test out. So
Another thing is too, you know, when I started wearing devices, I was born with one hand, and I never had a prosthesis growing up. And I started putting on Raptor hands, and how big did this? We have to scale after like what, a couple months.
Well,
I grew like 15%.
First was 128, and now you're up to 152. 153.
Yeah. So my arm has gotten huge compared to what it used to be. So that's another thing you have to consider. If you have someone with an acquired amputation, they may have the ability to have that musculature, and you know, also there's other comorbidities you have to consider with that as well. But for someone like me with a congenital amputation, it's kind of hit or miss because you don't know how much use they have with that arm, to be honest.
Well, so I am on the lookout for sockets that can be customized to your feet to your arms, the way we customize shoes to our feet.
Sure.
You pick the approximate right size and you tighten up the damn laces. This seems to have is this sort of spiral architecture your own innovation?
yes, so we were trying to basically follow the
It's first
structure.
like a more
Yeah.
like rectangular shape, and then we realized I guess we had to get more organic with it. If we're looking for those movements, you have to have something that moves with those natural body movements.
in the first
I
design.
want to encourage you to explore the possibility that small, medium, large, skinny, narrow, skinny, medium, and wide, with your adjustments, might be something that could be bought off the shelf and made use of. That would be huge.
Absolutely, absolutely.
So I don't know enough about anatomy. That spiral direction, does that follow sort of the path of the muscles in
So
your arm?
Yes. So in the first design, we were trying to follow the bone structure. So
Okay.
if you took a look at your arm, your bones travel in a spiral direction.
Can I get this one? So this is your ulna, right? Your ulna, your pinky
Yeah.
arm bone, right? This is your radius. This is your internal thumb base bone, right? So this is stationary, and when you pivot your arm, your radius actually pivots around the ulna. So if you see here, the material is kind of conformed linearly to the ulnar, but here it's kind of actually tracing a muscle group that goes across your forearm, which is responsible for those movements. So that's kind of intuitive where we're getting with the organic shape is we're actually tracing the musculature in reference to that bone, the ulna, as a reference.
So if your arm ended below, proximal to the wrist, how much pronation, supination could a person still do? You're getting a lot of
Are you
wrist
saying
movement here.
without wrist articulation?
Yeah.
So wrist disarticulation, it just depends really on their ability.
Yeah,
you know?
okay. I
This
haven't had
material
much
is
experience with it.
quite flexible, so you know if they have limited movement, it still allows for very.
So I just wondered how much they could do, like using a spoon
Oh
in
yeah.
soup and stuff like that. The pronation, supination is kind of valuable.
You kind of highlight another point too. So as a wrist disarticulation amputee, one thing that we have to consider is arm length. Now, if you're putting something on top of a distal appendage that's there, you may get some symmetry, but chances are you're going to put a handle there that doesn't fully match the length. So in terms of getting used to some tweaks and then learning how to use it, I think that's something that can be more to play into that. But
Now, do you have an attachment so that if Eric Luber shows up with his motorized
that's what I was
two tree or gripper
This
this
actually,
weekend?
so I found this DWG file. It's on Autodesk somewhere for the iLim e-Bionic hand. I found that, so you can print that.
Now, I'm interested. You remember from last year we had the FDA guy to give us a talk.
Matthew DePrima,
Yes,
yeah.
and you get the class 1
Oh, okay. You're talking about
exemption
Commander
if you
James.
use only 1 degree of motorized. degree of
Motorized.
freedom.
Motorized. That's
So-
that's the key word. So this is
So-
a passive
Yeah,
passive
so
socket.
you can do all
so
that.
you get all the
Is-
degrees of freedom,
Has
but
the
not,
big Bionic got more than 1 motor in it?
they have up to 27
sure.
degrees of freedom.
But if they only use one at a
But
time,
it has more than one.
we can
More
ask
than
them.
one at a time, right. So I guess what you're highlighting is the fact since this is a passive device, it's not incorporating a motorized component, but it's still allowing for multiple degrees.
Yeah, which is cool. So,
Under the radar.
so,
No.
So Luber's got a
That's not
design that he's going to show us hopefully this weekend.
Oh yeah.
It's only got 1 motor, and so he can pass.
Well, this is where all the housing also goes for like the batteries and such. The motors are all in the hand, but I think one idea was to incorporate a device where we're putting things closer to the body.
Yeah,
So,
yeah.
as far as weight and center of gravity, those issues. I'll tell you, when I put on the Bionic hand, I recommended that we get a shoulder harness too, just because I know I will fatigue after a while.
It's heavy.
I've got a bad back, so I don't know if you guys know that, but I got a bad back, and if you're pulling me to one side, then
Yeah, okay.
I can cause issues.
It looks like you could replace that DWG for the Bionic with a receptacle for a carriage bolt, at which point there's a gripper hand that would like to see how it feels in there, there's a...
I think that'd be a great way to really bridge. I would love to do that, yeah.
Backing you up on those sockets and a way of attaching devices or portions of arms that give you some degree of movement but also are interchangeable. That's really the grail of my things now.
Fantastic. Thank you.
All right.
Nice job.
This is a smart arm. This is a very smart arm. Why is this a smart
So
arm?
here's the other thing.
Why is this a smarter?
We're trying to integrate a haptic feedback system in this socket as well. So where's our finger? Finger's at.
So what he's saying is a haptic feedback means something that you contact and contacts you to respond to some stimulus. And the stimulus would be tactile touch in this case. So in the lab that he's working in, we are working on a wearable device. This is the first prototype you guys might have seen last year. But we're working on a second prototype to kind of allow the volume to fully what's the word? to kind of fit around the whole entire arm versus having a single bowl. Because one issue that we found is if you overstimulate, these things will blow up as they're silicone and they will pop. So we cannot have that happening. So Marty's his project this fall is going to be refitting it and coming up with the next version fit with the arm. And I think your idea was to kind of have it built in up here for one model, and then eventually having it actually in the appendage, so closer to those nerve groups that your body would recognize as touch in the arm and distal arm. We're going to try to put the feedback there so it's hitting the same potential spots.
So, on the hands right now, we have these locomotor sensors that use resistances to basically imitate sense of touch, and
Pressure, heat.
and from that we are able to pass that into the computer, go to the software, and basically pump these bad boys up and feel.
So it's a pneumatic system, uses air power for that.
Yeah, is it pressure, heat, does pressure kind of sense? What type of?
So that one is a liquid sensor. That means when so it's embedded. If you're going to see it, it's embedded in a sort of gel type material, and once that gel flexes, it's going to stretch that liquid metal, and when it stretches, the resistance, the electrical resistance of that metal will change, and we can measure that resistance and see how much it's changed, and then basically that's how we are able to tell.
Oh, no, yeah, so it's pressure. What would the user feel? That's what I was asking. So pressure, not,
Yeah, pressure.
it would be a sense of pressure.
What kind of silicone are you using for
That is
EcoFlex?
no. So we just adopted a new type of silicone. I'm not too sure, but I can tell you what this one is. It might be EcoFlex. So there's two different types of material in this one. There's Dragon Skin and there's EcoFlex. Yes. So EcoFlex is a little more flexible than Dragon Skin. Dragon Skin is sort of like just tough. So the base here is made out of Dragon Skin, and the top bubbles here are made out of EcoFlex. So it's able to stretch a little bit, and I guess it's not strong enough. So in the next version, we're going to try to reinforce it with some flexible filament inside there, like NinjaFlex.
That was a very interesting trial on that day. Any other questions? No? All right, yeah, we'll pass it.
Does anyone know? Are you back? Does anyone